Hi, I'm Teresa from VLab at EPFL. I'll be presenting our work titled Robustness via cross-domain ensembles. This is joint work with Oğuzhan and Amir. We have a project webpage where we have more qualitative results, links to our training code to download pre-trained models and baselines. Neural networks in the real world will encounter data with distortions, such as defocus blur, JPEG compression, or adversarial shifts. For example, the first column shows a clean, undistorted image, and the corresponding surface normal's prediction of a standard network. Under slight distortions, the second and third column shows the predictions of the same model. The ground truth is shown on the bottom right. As you can see, seemingly small and non-adversarial image distortions cause large errors in the neural network prediction. The errors in the predictions get worse as the distortion intensity increases, as seen in the plot in the top right. This is the challenge that needs to be solved for models to be useful in the real world. Our proposed method is based on ensembles. The core idea behind ensembles is relying on the diversity of individual models to decorrelate errors. Sources of diversity include using different initializations like deep ensembles, different hyperparameters, network architectures, or by modifying the training loss. Our method is based on making predictions from a diverse set of cues that we call middle domains, and we merge the predictions based on their uncertainties. This is how our method works on a single image. Given the distorted input image where the distortion is JPEG compression, we extract the set of middle domains. Examples of these middle domains are 2D edges, low-pass filtering, grayscale, and embossed filtering. Note that these middle domains are programmatically extracted, so they do not need any labels, and they can be obtained for any dataset without supervision. Given middle domains as inputs, we learn to predict the final target domain, which is surface normals here. Each middle domain has corresponding predictions define a path, and as you can see, each path reacts differently to a particular distribution shift, so the prediction quality will differ among paths. In this case, the low-pass filter path does not degrade as much as the others. To obtain uncertainties, we model the network output as a Laplacian distribution with parameters mean and sigma, where mean is the prediction and sigma is the corresponding uncertainty. We then train the network with a negative log likelihood loss. In the uncertainty shown here, darker means more confident. We convert the uncertainties to merging weights by taking the inverse of each path's uncertainty. The idea is that each path will contribute to the final prediction based on its uncertainty. For example, this path has degraded predictions, thus higher uncertainty, which results in lower merging rates compared to the other paths. We merge the predictions from different paths by using the merging weights, and this is our final prediction. We have seen an example on a single image. We will now see how this works on the short video clip. Our ensemble has 8 components resulting in 8 paths. These are their predictions, corresponding uncertainties, and weights. The final prediction is shown in the top row. See how each path prediction differs. For example, the low-pass path has lower uncertainties with more accurate predictions on the floor. This is also reflected in the higher weights. Remember that we model our output as Laplacian with parameters mean and sigma, where mean corresponds to the prediction and sigma is the uncertainty. As shown in the video, our method relies on the uncertainty estimates to merge predictions. However, uncertainty estimates are uncalibrated under distribution shifts. In other words, there is a high tendency to output poor predictions with high confidence. To calibrate the uncertainties, we propose an additional training stage that we call sigma training. In this stage, we feed the network with out-of-distribution inputs. We train with 2 loss terms. The first term helps sigma to increase when faced with distorted data, and the second term helps to keep predictions fixed. This is an example of overconfident and incorrect predictions. The image has been distorted by different levels of speckle noise, and these are reshaped predictions. Before sigma training, when the model produces poor results, the uncertainty does not increase correspondingly. The same goes for the uncertainty produced by deep ensembles. After sigma training, uncertainty estimates are better calibrated to account for degraded predictions. Notice that our predictions do not change after sigma training if you compare the predictions before and after. Sigma training, they are the same, but uncertainties are higher. Hence, the uncertainties have been successfully calibrated. We quantified this with a scatter plot here. It shows the error against average sigma. Each point is an average over 16,000 test images for one unseen distortion and one severity level. Before sigma training, sigmas do not increase with an increase in error, and this is the same for deep ensembles. After sigma training, there is a stronger correlation with uncertainties and error. Now for some results. We obtained improvements in robustness compared to several baselines, under non-adversarial shifts and adversarial ones, for several tasks and datasets, like regression on Taskonomy, Replica, and Habitat, and classification on Imagenet and CIFAR. So unlike most existing works on robustness focusing on low-dimensional prediction tasks like classification, we also experiment with dense pixel-wide tasks. Let's look at some qualitative results. Each row shows an image from the Taskonomy test set under increasing speckle noise. These are the results for the reshading task and the corresponding ground truth for comparison. Our method degrades less than deep ensembles and using a single model. The difference is obvious at high distortion intensities. This is for surface normals task. The same trend holds, our predictions do not collapse as quickly as the baseline. Finally, for depth estimation, this demonstrates the effectiveness of using different middle domains to obtain a robust prediction. More qualitative results under 4 distortions: impulse noise, defocus, blur, contrast, and pixelate on a sample image from the replica dataset with the same distortion level. Each prediction is followed by its corresponding error map, and for pixelate, the improvements over ensemble and single model is obvious. For the other distortions, we circle the improvements in fine-grained details. More qualitative results on a YouTube video. This video has been corrupted by increasing shot noise. Our method returns more accurate predictions with less flickering. These are the quantitative results for common corruption distortions applied on the Taskonomy test set for surface normals prediction. Each point shows the error averaged over 11 unseen distortions. Lower is better. Some of the baselines worth mentioning: yellow is a single model, dark blue is deep ensembles, light blue and dark brown are single models but with data augmentation, where light blue is adversarial training and dark brown is with style data. Red is our method, which clearly outperforms the baselines. Purple and green are variants of our method, where purple variant learns a merging function and green is a simple average. The trends are similar for depth and reshade task too. Deep ensembles have a similar performance compared to using a single model, even though augmentation methods such as adversarial training and style are competitive baselines. Our method has stronger performance compared to them. We also have quantitative results for the same task on other datasets, such as Replica and Habitat in the supplementary material. The robustness of a method is not limited to non-adversarial shifts. The video shows an image under a text generated by IFGSM under increasing attack strength. Our method is more robust to attacks compared to baselines. We also quantify the adversarial robustness of a method under different attack strength with L1 errors. Lower is better, and our method used lower error compared to baselines. We believe that this is because using middle domains promote ensemble diversity in a way that makes it more challenging to create an attack that fools all paths simultaneously. We have some ablation studies. This one looks at the effect of increasing the number of paths and the roles of uncertainty on performance. This is performance on out-of-distribution data. Each point shows the average error over all combinations of a fixed number of paths. For any given number of paths, our method shown in red consistently outperforms deep ensembles shown in blue for all 3 tasks. This also implies that performance is not sensitive to the choice of middle domains and the performance gap increases with more paths. Compared to a variant of our method, uniform merging shown in green, which does a simple average of the predictions, Merging with uncertainties further boosts performance. This is another ablation study to analyze the importance of each middle domain. The chart has 11 axes. Each one represents one distortion. Each curve represents a middle domain prediction path, so there are 8 curves. A curve gets 1 on the distortion if it contributes the least and 8 when it contributes the most. For example, the direct path, which is a mapping from RGB to the target task, is most helpful for saturate, and to the edges was the least helpful. We see that the low pass middle domain was most helpful for noise distortions, and the sharpen domain was most helpful for contrast distortions. Our method is not limited to pixel-wise regression task. We show the results here for ImageNet classification under clean and distorted data. The second column here is the error for clean data. We also show the individual errors from each distortion from the different categories: noise, blur, weather, and digital corruptions. Average here is the average of these numbers. Our ensemble predictions are just a simple average of the predictions from all paths. The only difference between deep ensembles and our method is the use of middle domains. We also have supportive results on CIFAR 100 and CIFAR 10 in the supplementary material. To conclude, using middle domains promote ensemble diversity, which improves performance by decorrelating errors, and it has negligible increase in computational costs compared to deep ensembles. Uncertainty-based merging allows the method to select regions from the best performing path. We obtain improved robustness compared to baselines under distribution shifts such as common corruptions or adversarial text for both classification and pixel-wise regression tasks. And this improvement in robustness did not come at the expense of the performance of in-distribution data. Thank you for listening. Visit our poster or come and chat with us if you have further questions.